Hello, everyone. I'm Whitney Espick, CEO of the MIT Alumni Association, and welcome to November's MIT Alumni Forum. Energy for Tomorrow, MIT's Plasma Science and Fusion Center. Fusion energy is experiencing a surge in popularity, fueled by strong interest from both the private and public sectors, along with a wave of innovative startups and government-funded projects. In September, the MIT Energy Initiative and the MIT Plasma Science and Fusion Center, known as the PSFC, released a report highlighting fusion's potential to contribute to future electric power systems. As global electricity demand rises, there's pressure to decarbonize to meet net zero carbon goals, and this report indicates that fusion has the potential to lower decarbonization costs by trillions of dollars. Today's speakers will discuss how the PSFC can help shape fusion's future and the potential to meet net zero goals amid a period of unprecedented interest in fusion. Nuno Loureiro is a professor of nuclear science and engineering and professor of physics and director of the PSFC. MIT alumnus Zach Hartwig, PhD 14, is an associate professor in the Department of Nuclear Science and Engineering with a co-appointment at the PSFC. Professors Loureiro and Hartwig will be joined in conversation with our moderator, MIT alumna Sarah Ferry, a 2011 graduate, also SM16 and PhD 18. Sarah is a research scientist and the group leader of fusion materials and components at the PSFC. If you already have questions on this topic, don't wait. You can start adding them to the chat box below. You can also upvote questions to help ensure that we speak to what's on your mind. And now I will welcome Professor Loureiro. Thank you and enjoy.
Well, good afternoon, everybody. It's a pleasure to be here to talk about the exciting research we're doing at the PSFC. It's a great opportunity for us to showcase cutting-edge research trying to advance fusion energy for a better future for everybody. I'm going to share some slides with you for the first part of the presentation, and then I'll introduce my colleague, Professor Zach Hartwig, who will do the second part of the presentation. Here we go. So in preparing this presentation, we were mindful that not everybody in the audience is necessarily familiar with fusion. And so some of the material here is at a relatively basic level, but we're happy to get into more technical questions at the end during question time. So many of you know that fusion is the process that powers stars. So the reason that they shine is because at their very core, there are fusion reactions going on that essentially release the energy that keeps the stars alive and shining. We speak of the plasma state of matter as the word that best describes the state at which the matter is at these very high pressures and temperatures that you find in the core of stars, such as the sun. And so essentially, in a sort of a slogan kind of way, what we're trying to do at the Plasma Science and Fusion Center is to recreate star-like conditions on Earth, aiming to tap that energy, the fusion energy, for electricity or energy production. So in case there's questions about why we're trying to do this, there's a long list of reasons that range from no polluting emissions to inexhaustible fuel supply, very energetic reactions. So, 10 to the 7 more energetic than a chemical reaction. No risk of meltdowns or long-lived nuclear waste, civilization scale energy, and flexibility to generate fusion energy pretty much anywhere. So this is a set of reasons that are very compelling, considering sort of several aspects, including not just the physics and technology, but also sort of geopolitical situations. Now, the sun is very good at doing fusion because it is so big and massive. So its gravity creates at its core the pressure conditions that are necessary to overcome mutual repulsion of the nuclei that you want to fuse, Coulomb repulsion. So the question then is, how do you recreate that on Earth? So we don't have the luxury of such intense gravity fields. And instead, what we do is we try to approach it with magnetic fields. So we use magnetic fields to control particles' trajectories so that, if you put a plasma in a vessel of some form, you avoid the particles touching the walls by essentially trying to guide their trajectories using very cleverly designed magnetic fields. And that, of course, speaks immediately to the need to be good at creating magnetic fields, something that you'll hear more later on in this presentation. And so if you look at the figure on the left, you see essentially a section of a cylinder threaded by a magnetic field. This would be fine, perhaps, if you could afford to have an infinite cylinder, but that's impractical, obviously. So instead, the solution is to fold the cylinder onto itself and create something that looks more like the figure on the right, which is a donut-shaped device, toroidal device that we typically refer to as a tokamak. This isn't the only way. So in the news recently, or over the last few years, especially more than in the past, there's been a lot of talk about inertial approach, the inertial confinement fusion, such as pursued at Lawrence Livermore National Lab in California. This is a completely different idea. This is the idea that you can use lasers or X-rays created by laser shining on a surface to compress a small pellet, a peppercorn-sized pellet, compress it down to the pressures necessary to initiate the fusion process. And on the right is an actual photograph of what the chamber of the National Ignition Facility looks like. And you have to imagine that at its core, there is a small pellet that's being irradiated by 192 laser beams. Now, achieving net fusion energy is an enormous scientific and technical challenge. And, the testimony to that is how long it's taken for us to get to be where we are. This challenge is one that spans many disciplines, ranging from theoretical physics, so the physics of how plasmas or matter in the state of plasma is confined in these oddly shaped magnetic fields, all the way to very difficult engineering and technology problems, such as how do you build the necessary magnets, how do you heat your initial gas to the temperatures that are necessary for fusion, heat transfer between the plasma itself and the materials, shielding from the neutrons that arise in the fusion reactions, the best materials to withstand neutron fluxes and heat fluxes, etc. So this is a very complex operation and requires sort of engineering, sort of industrial scale capacity to advance towards a solution. And these are illustrations of the two sort of bullet points here. On the right is a direct numerical simulation by a colleague here at the Plasma Science and Fusion Center of what turbulence might look like in a fusion device, and our need to understand this turbulence at a predictive level, because essentially this turbulence controls how hot you can get your plasma to be, and that's essential. And on the left is a picture of my colleague Zach Hartwig working on the new magnet technology that he and his team developed, and which became the backbone for the sort of success that we're seeing now with fusion startups, or with some fusion startups. So hopefully this introduction gives you a sense of what's needed to arrive at fusion technology and fusion energy. And on the right here, I'm showing you a picture of what the Plasma Science and Fusion Center is. So all these buildings that are highlighted in red are the PSFC. Inside of each one of these is our state-of-the-art teams working on different aspects of fusion energy and fusion science. We've been around since 1976. We have very significant square footage on campus. This is probably one of the biggest academic scale operations worldwide, even. We have roughly 150 employees, something like 90 graduate students, many ongoing research projects that touch on different aspects of fusion energy. Now, the reason that we're having this talk now and not 10 years ago is that the world of fusion is unrecognizable as of 5 years ago. Essentially, this change has happened because of technological successes that were spearheaded here at the Plasma Science and Fusion Center. And the center to those technological advances are new magnet technology and a series of other technologies that allow us to now be much more confident about where the fusion energy field is going. We launched the MIT CFS partnership about 6 years ago. So CFS is a private fusion startup here in the suburbs of Boston, so Devens, Massachusetts. And their success has changed the way that philanthropy and venture capital thinks about fusion, and really, I think, has seeded an avalanche of fusion startup companies and changed how the world is viewing fusion and how close we might be to fusion energy as a reality. And the goal for all these companies, as well as for us at the PSFC, is to bring fusion energy to the world as soon as possible. So I was just saying the fusion startup industry has exploded, and this is a plot, well, it's a chart of some of the fusion companies that exist throughout the world. This image is outdated almost the moment you make it, because this field right now is so vibrant that almost every 2 weeks there's a new fusion company. And the numbers are also outdated. On the right, overall in the US, over $8 billion have been raised of private funds for fusion startups. There's now an industry association. You're seeing, I think the US perhaps is leading in terms of fusion startups, but you're seeing fusion startups in other geographies as well. And it's probably clear to everybody that not all of these companies are going to survive, but competition is good, right? So we don't yet have certainty on which model or which concept is going to be the winning concept for fusion. And even among similar concepts, just having competition, I think, stimulates a type of environment that you couldn't even dream of 5 years ago. And that's a real breakthrough in itself. Governments, of course, are paying attention to this. So a couple of years ago, the White House announced a bold decadal vision for commercial fusion energy that they've backed up with new funding streams, mostly aimed at stimulating public-private partnerships. So at the bottom here are the names of companies that were selected by the Department of Energy to spearhead some of these developments in the public-private partnerships. And the PSFC has a very strong connections to several of these and others that are not on this slide. It's not just the US that's paying attention. So internationally, fusion efforts are growing in magnitude and scope. For example, in the UK, 2 years ago, the UK government pledged over $250 million for a pilot power plant concept design. And they're now going to move forward with actually building this power plant. China, of course, is also very active in this field. They're moving very fast. They currently outspend the US in fusion research. Japan is also realigning their strategy to make sure that they advance towards fusion power plants as swiftly as possible. And I think most surprising, at least to me, was that there is now a G7 initiative to establish a working group on fusion energy. And in fact, just last week, I was in Rome to attend the first meeting of this working group. This was a ministerial level meeting co-hosted by the Italian government and the International Atomic Energy Agency that gathered representatives from governments around the world, as well as industrial partners, fusion startups, and fusion technical people from national labs and others like the PSFC to sort of sit around the same table and discuss what the fusion industry needs to look like if we are actually going to be serious about deploying fusion energy at scale, as well, of course, as overcoming the remaining technical challenges. So this is where I'm going to hand off to my colleague, Zach Hartwig, who will now focus more on specific projects that we're pursuing here at the PSFC.
Great. Thanks a lot, Nuno. So thanks everybody for having us and attending. So what I wanted to do was kind of jump off from what Nuno presented and show you a segment of what the PSFC is doing. And it's primarily in the area of developing essentially the technology that we're going to need to deploy in order to turn fusion from a very interesting science experiment into a commercial energy technology. So let me share my slides with everybody and sort of see that by the title. So the idea is kind of how do we think about tackling fusion technology on challenges on rapid timescales. And, this is really important. As Nuno pointed out, there's now a nascent fusion energy industry. There's $8 billion. There's a tremendous societal demand for energy. And all of a sudden, something that has been a physics experiment, fusion, for a long time is now really being pulled into and expected to be an energy technology. And in some ways, we now have to catch up to that expectation. So what I wanted to do was kind of give a sense of maybe 4 of the major systems or technologies that are required to take the star on Earth and actually create power, something practical that we can do. And so this is a picture of a tokamak, sort of a fusion power plant, if you like, where in the center of the device is the plasma, the 100 million degree piece of the star. And I want to touch on 4 different technologies that are needed. One is high field superconducting magnets. As Nuno mentioned, we need very powerful magnets to confine the plasma in magnetic fields and suspend it, hold it away from the walls and the other materials so that it has high performance. We need to actually, build those magnets and build the device out of something. So unlike space where the star sits in a vacuum, nice and happy, we actually on Earth have to put it into something real, something made out of Earth stuff. So structural and functional materials are going to be necessary, not just to build the device, but also to make sure it operates robustly and economically at the end of the day. We have to produce power cost effectively, and materials are going to be at the heart of that. The 4th bullet, which I point out here, is the injection. How do you heat these plasmas? How do you sustain 100 million degrees? In part, that is done with an external power source, radio frequency power, RF heating. And so we need to inject power into these plasmas through RF antennas and other types of high power RF technologies. And then the 4th is actually how we convert the fusion energy into electricity. Essentially, we need to make heat. That heat is useful for doing things, one of which is electricity. And the other is we need to generate fuel for the plasma. We do that in something called a blanket system. And in thinking about how to go through these 4 things and how to actually pack all this into a relatively short 15-minute talk, I wanted to come up with kind of an interesting way to frame the talk. And I thought what we'd do, since we're all MIT people, is we'd run an experiment. So we'll propose a hypothesis, and then we'll test that hypothesis. It's really like an experiment because I know the outcome, but it'll be fun to run it and see how we do. And so I thought what I would do is kind of challenge people to think back on their time at the Institute and your interactions with the Institute, and think about what it takes to really make impact. And I'll propose a hypothesis that impact occurs, real impact, when we have these 3 ingredients present in the research. One is a framework. It's not just the research, it's actually how the research is structured. How is it funded? How do we translate the work that we as faculty and scientists and students do at the university out into the real world? That's ultimately, I think, many of our goal here at the Institute, is to get that research out of the lab to have impact. So we need the right framework. We need to do the research, of course, so we have to be able to fluidly execute the research with the technical excellence that's at the heart of MIT. And I think the third thing is what I'll call synergies. So the opportunity that we have to construct to import and export learning. We have to bring in learning from other fields, and then we have to be able to export that learning to other places to create sort of more of a synergistic network of fields that are sharing knowledge and pushing themselves forward. And so what I wanted to do was show you how the PSFC has actually sort of used this approach to build its research program in fusion technology and how that's helping us go faster towards fusion energy. And so I put this slide together because I think if we zoom out sort of the 10,000 foot view, what I touched on with framework is really important. And I hope many of the people here, many of the alumni have had a chance to interact with one of these very compelling and powerful experiments over the course of MIT's lifetime. And I always like to make the point that MIT, I think, is at its most successful when it's actually inventing the medium in which it's doing research. And there's a bunch of examples up here on this timeline, going all the way back to Van de Graaff down here at the bottom left, building one of the first particle accelerators, to things like Lincoln Labs, Draper Labs, Whitehead, the Alcator CMOD experiment that we ran here, all the way up to MIT Nano and LIGO. It's actually the framework that are behind these major research initiatives that enabled them to do the research itself. And I think that's really important. I really love this quote from former President Reif that said, MIT's greatest invention may actually be itself, an unusual concentration of unusual talent, restlessly reinventing itself on a mission to make a better world. So it's the way we do research in addition to what we do that is sometimes equally, if not more important. And so what I wanted to try to do is show how we're doing that in different areas of fusion technology. And I'll have to do that relatively quickly. So the first is to touch on that initial challenge of building magnets in order to confine the plasma. So how do we actually accelerate fusion and launch an industry while creating the magnets necessary? So on the left, this is a picture of ITER. This is a experiment that's being built by about 30 nations around the world that'll be deployed and turned on, hopefully producing net fusion energy in the late 2030s. This has been the sort of the focus of the government-funded program. And so you can see in the middle of my slide, here's the human for scale. And this is a big device. It's taken decades to build. It'll cost tens of billions of dollars. It does nice physics, but it doesn't exactly look like something that might make cost-effective electricity in a quick period of time. So what can we do about that? Can we make it smaller, cheaper, faster, sooner, being able to be built by a company, not 30 national governments? And so here, this is a plot that's essentially boiling down 60 years of tokamak physics into a single plot. And what is it? It's the magnetic field, the strength of the field that we use to confine the plasma. This is the size. Think of it as the linear size of the device. And these contours are physics, predictions for how much gain we get out of the system. And of course, if we want to build a power plant, we want to be up here. We want to get many times more energy out than in. ITER is right here in this design space, if you like. Because of the magnets it uses, ITER has to be an enormous device. It's just what the physics tells us. And so in order to get much, much smaller so that we can go faster, we can go cheaper, we can build multiple devices and iterate quickly to success, what do we have to do? We have to develop much better magnet technology. And that essentially was what was done here, starting about 6 years ago, as Nuno mentioned. And it was really two things that happened here that I think are worth mentioning. The first is the actual technology. So the actual technology that we brought largely from outside of the traditional fusion field and injected that into fusion research on magnets, combined with significant amount of capital, and really a higher appetite for taking on technology risk than what was currently being done in the federal programs. It's a very MIT thing to do. And we were able to basically, in a period of about 3 years, go from benchtop scale prototypes all the way to fusion scale magnets. And that's what I'm showing a picture of here. So this is a picture of the spark toroidal field model coil and the overarching test facility that was built over 3 years that allowed us to deploy this magnet technology. The other thing which is really important is, again, not just the technology, but it's actually the framework that enabled this to be done. So using a $1 million gift from an MIT alumni, one of you, we were actually able to jumpstart the research program here at the Plasma Science and Fusion Center. And after a few years, then spin out Commonwealth Fusion Systems from the lab as a private company that could take large investment, partner with MIT in a very deep and sort of integrated way to basically do large-scale R&D from the moment it was founded and to deploy this technology on short timescales. And so here's a picture of the team that I oversaw building the spark magnet program. Commonwealth Fusion Systems and PSFC, MIT and CFS people working side by side on a joint venture. And because of that success, CFS is now a company of 1,000 people. They've raised $2 billion, and their focus is on commercializing fusion. Meanwhile, PSFC retains its status as an academic and thought leader in the world of fusion energy research. And so that's really our mission now, is to help CFS, but to help other companies go forward. And of course, there's always interesting synergies from what we've done. So taking the magnet technology and spinning it out into things like next generation physics experiments. So the next thing we want to tackle, since magnets is up and going and we have research programs, is materials. And someone once said to me recently, if fusion energy is an energy technology, that means it's a materials problem. So as Nuno pointed out, we have 40 companies. They're all focused on pushing fusion power into the 2030s, and national programs are supporting this. All of these approaches, doesn't matter what it is, has materials challenges at the core of not just demonstration, but ultimately economic viability. And there's presently, in the world of fusion or elsewhere, no fast track and scalable approach to developing these materials and qualifying them for the environments that they need to be in. So what the PSFC is doing is, again, trying to rethink of the framework that we're going to make to enable the research and then to go off and execute that. And so what we're doing now is building a unique facility, which is shown here on the right, where we have a high power accelerator known as a cyclotron, injecting beams of particles into materials in complex environments that replicate what they'll experience in a fusion device. But we can actually effectively age those materials up to 100 times faster than they can be aged in application. And how are we actually doing that? Well, to build the facility, we want to go as quickly as possible. We have to start answering companies for the fusion companies. So we're reusing about $50 million of unused existing MIT research infrastructure that was brought here as part of prior public funding through Department of Energy and others. And we're actually in the process of raising philanthropy from alumni and from donors, again, to kind of kickstart a major effort here to do something a little bit different risk appetite and a different speed than what can normally be done in government-funded research. And then, of course, we're going to have to operate it. And so what's being put together now is a very interesting model. I'll call it the P3 model, where we're combining public, private, and philanthropic money all together to sort of maximize the reach, but also the speed that we're able to do science and translate that science out into the laboratory. And of course, doing it at a place like MIT means we can integrate it, deeply into the institute and beyond. So this is going to be embedded in the heart of the MIT material science ecosystem. We have undergraduates and graduate students who will be an integral part of doing the research, but also operating a world unique facility. And that's really important for workforce development for this emerging industry. And it also means we can utilize, fusion to actually help bootstrap other technologies. This is that exporting the learning. So the idea of using such a facility to advance nuclear power, develop new quantum materials, help enable high energy physics collider experiments that are going to replace the Large Hadron Collider. These are all things we're now talking about with people within the Institute and outside the Institute that the facility should be able to do. And we hope to see this facility up and operating sometime in the next year and a half. Now, there's other things which we're doing that we want to think hard about using these new models and the learning that we had from them in order to scale up. And I wanted to mention two of them. One is this high power RF technology. So we need to be able to inject high power into fusion plasmas. And we need to be able to do that while those materials and the technology is right up against that 100 million degree plasma. So one of the ways that the PSFC, who's at the forefront of this technology, is pushing things forward is actually doing things like additive manufacturing of very complex RF technology in single piece monoliths using techniques that have been developed in the aerospace industry, novel high performance copper alloys. And as you can see here, actually a 2 foot by 2 foot bed where we can 3D print with exotic copper alloys that can withstand the fusion conditions. And this is a picture of one of our research scientists installing that on a fusion device in California called the D3D tokamak. So this will be the first time ever that such a technology has ever been deployed in a fusion system. And this technology, again, to go back to the synergies, is very complementary with what we want to do in fusion, but also in other areas of energy. So, there's an idea for scaling this up in the way that we've done for magnets and the way that we're doing for materials. Really putting together a vision for sort of an industry scale additive manufacturing, materials printing, and RF test platform at PSFC. So we can do things at a much bigger scale than other of our peer institutions. But also there's interesting synergies to explore. So one of them that's being explored now is something known as deep borehole technologies. How do we actually drill down 10 kilometers in order to tap into the geothermal energy that exists at those depths? It's an incredibly hard problem to tackle mechanically, but with RF and plasma technology, turns out we can do that. So here's some pictures of real rocks that have actually been drilled using RF technology at the PSFC. One interesting application is actually drilling those holes and opening up new sources of clean energy for geothermal. Another very interesting one is shown here on the right, which is actually using the very similar technology to actually go down and seal off old oil boreholes that are currently leaking. So there's very much energy and environment spin-off applications which are coming out of the fusion research that we're doing. The final thing I want to mention before we sum up is, again, this idea that we need to develop a technology that's going to allow us to produce power, something useful from the fusion, and also to generate its own fuel. So, as Nuno mentioned, we have to convert hydrogen, effectively, isotopes of hydrogen, deuterium and tritium, into fusion in order to make energy. And so the fusion reaction that we use produces a neutron, and it produces a helium particle. And it's really the neutron that we want to focus on. Ultimately, what we need to do is take that neutron and send it into materials that are going to do two things. One is they're going to convert neutrons into tritium through lithium reactions. So we need materials with lithium so that we can generate the fuel that we use to drive the fusion reaction. And then we also need to capture that heat. So we can use industrial quality heat for electricity, hydrogen production, smelting copper, many other things. And one of the reasons this is important, if we want to think about fusion as an energy economy, scaling up to meet demand, is that it turns out if you look at the time scale for deploying fusion power plants and how much power we can put on the grid, the real limitation to scaling up is how much tritium we can make. And so if we can't make tritium fast enough, it's going to take a long time, even if all the other parts are in place to deploy more fusion technology plants. So we need to get much better so that we can actually open the pipeline for how much fusion technology we can put on the grid. And so we have an experiment now. This is actually led by Dr. Ferry and her colleague, Dr. Waller at the PSFC, where we're starting to do integrated tritium production experiments at the PSFC. But there's very much a vision for going from beyond where we are today into much larger scale breeding experiments, and maybe even ultimately a full scale fuel cycle experiment that replicates the entire parts of this, but decoupled from a pilot plant, a fusion plant. So we don't have to wait to get going. And of course, there's a lot of synergies that we're looking at exploring around the Institute, thinking about tritium for neutrino physics with the physics department, or SALT for nuclear power. So I think just to summarize, that's a lot to pack in, but to summarize, essentially the PSFC is thinking hard and building creative frameworks for executing the research that we need to help drive the fusion industry forward. And one of the things I take away from this is the demands for climate solutions and the willingness for investment in high-risk, high-reward technologies like fusion is opening opportunities, and the PSFC is really seizing them. Another big takeaway is that bold, mid-scale, creatively structured, university-based research programs are accelerating timelines for fusion and other zero-carbon energy sources. We, MIT, can really play a difference in pushing things forward and moving the needle. And what we're doing here is just one example of a number of them across the Institute where MIT can be doing these types of things to fight against climate change. And the last thing is, just because I have the platform, I just want to share a thought, and maybe people can ask questions. But I think there's really an idea that fusion is a part of many other technologies, which is solving the societal scale problems in front of us. in the 21st century. The extent to which we are successful is going to be defined by what we choose to build. And so the PSFC is ultimately about building things that are going to go out and have impact. And I'll leave you with one of my favorite quotes from all time. This is actually a picture from the Library of Congress in the entrance hall. And it's a quote from the poet Edward Young. And it's, "Too low they build, who build beneath the stars." And I think that's the kind of vision that we have to have at MIT to go forward into the 21st century and use what we know to solve problems. So I think with that, hopefully we're close to time, and I will turn it over to Dr. Sarah Ferry, who will moderate questions. And I think Nuno and I look forward to hearing from you and trying to answer your questions. Thank you.
All right. Thank you, Zach. Thank you, Nuno. So we have a lot of good questions in the chat so far. But just to kick it off, I think we have a fair number of alumni currently on the call who were involved in fusion research during their time at MIT in some ways. So just to pick one of them, we have an alum who was here in, let me just find it really quickly, who worked on Alcator C as an undergraduate in the 1970s, Zach. And so I just kind of wanted to highlight that because this person is asking, what is the status of that machine? But it's actually sort of a nice tie-in to the new cyclotron facility that you were talking about. So maybe just to kick it off and to sort of highlight some of the progress and the evolution of the PSFC, you can maybe talk about a little bit of Alcator C and CMOD and then how that has now led the way into this new project that we're working on.
Yeah, that's great. So, hello to whoever you are. It's awesome to hear there's people who are working on those devices. So the PSFC, just for everyone on the call, the PSFC has operated a series of fusion devices, starting with Alcator A, and then Alcator C, and then Alcator C mod. Don't ask me about the numbering. That's a whole history in and of itself. But what these basically ended up being were major scientific facilities that competed at the global scale that were hosted at a university. It's actually pretty unusual to have the types of experiments that are punching well above their weight for a university scale experiment at MIT. And what it meant was not only did MIT occupy a prominent role in the fusion landscape, but it also meant, I think, Sarah, to your question, that there was a tremendous amount of investment in infrastructure, in people, and in capability that still exists to this day. So I guarantee you there are people who worked with the person who asked this question who were deeply involved on the toroidal field model coil, for example. And those same people are going to be deeply involved in setting up the new cyclotron facility and in some of the other areas I mentioned. And so I think, I got to give a talk on this at IAP. One of the real values of the Alcator program and all the other things, and the real value of the PSFC is it's not just one project here and there. It's not a small research group doing something. It's this long, long line of research, science, students, capability that goes all the way back to the 1970s. And we're still leveraging that today. It's actually a really powerful thing for us to have in our pocket. And the fact that so many of the alumni who participated in that are still engaged is a great example of even sort of a further network that's still supporting fusion research at MIT today.
Sure. And then, but also just the fact that without the facility that we had built for those tokamak experiments, it would be a lot harder to build the cyclotron facility that we're planning now. So we're actually repurposing that space in a really exciting way.
Yeah, absolutely. I mean, so much of the infrastructure that is here that goes back to the 70s is being repurposed in different and sometimes unexpected ways. But that's exactly right. It's amazing to be able to go to philanthropists and to alumni and to say, guess what? We have this idea for a facility. We need your help, but we don't actually need $50 million to build a new facility. We don't need the 3 or 4 years to build that new facility. We don't need all those things because we already have them. We have the people ready to go. We have the students excited and applying. We sort of have it all. And it means we can go forward quickly and confidently to execute.
That's right. So I think maybe we'll zoom out a little bit and ask sort of some of the big picture questions that I think I kind of keep seeing come up in the chat, and then maybe we'll go from there into maybe some more like technical questions. But Nuno, something that has come up, and I think you both sort of addressed this in your presentations, but maybe if you just wanted to summarize, we all know like the cliche of fusion being just around the corner. So in your opinion, like what has changed to make this moment so different that we are seeing significant interest, both in terms of private funding and in terms of research development for fusion technology?
Sure. So I'll address one part of that, and then maybe Zach can address the second part. I think, over the last 20 years, the progress that we've made in understanding and developing truly predictive power over plasma behavior in a fusion device has increased, enormously. So we're now in a situation where, via a combination of advances in the theoretical understanding of plasmas and advanced computing, and more recently tapping into machine learning, we have a very thorough understanding of how a plasma in a fusion device behaves. And that's been instrumental in sort of allowing us to say, well, if I design a new machine that I haven't seen before, I expect that it will behave in this way and not that other way, right? So that has guided the design process and emboldened us to say, well, maybe we understand this process not completely, but well enough that we can make predictions about what's going to happen if I build a new experiment. So, and this is really, it's been over the last 20 years because these problems are very challenging, and the computational power that you need to solve them just wasn't there, before the 2000s. And so these 2 decades have been sort of very special in that sense, in this sort of combination of advances in theoretical understanding coupled with advances in advanced computing. So that, I think, is a strong reason to think that we are much closer now than we were before, because we have that understanding. But of course, 20 years later, there is a wealth of data that allows us to sort of, again, be able to understand better how a fusion device operates and guide those projections. But we also understand, I think, better what our technology needs are and where we need to improve. And guided by those advancements, in theoretical understanding of how a fusion plasma behaves, it was, I think, clear at some point that if you could increase the magnetic field that you use to control a fusion plasma, you would stand to benefit not linearly, but much more strongly than that. And so that's where the PSFC team, Zach Hartwig and colleagues came in developing what I think is, you may not say it, but I'll say, a truly revolutionary technology in how you develop magnets for fusion plasmas. So, Zach, I don't know if you want to say about that part. So the fusion technology developments that bring us closer to fusion power as a reality.
Yeah, I think that's right. From my perspective, I'll maybe offer 3 different reasons why things are different. I think one, just to emphasize it, is actually that the magnets that we've developed make fusion 10 to 20 times smaller. And that's significant. Fusion, cost scale like the volume of something. And so when you make something 10x to 20x cheaper, that's an order of magnitude transition in what is possible, not only in terms of schedule, but in terms of who can do it. So rather than the organizational complexity of 30 nations building fusion, we now have one company who's making decisions, for example. And I think that really does change things. Scale has changed completely, and that's important. And there's other examples in technology where that's true. There's 2 other things that we can't really control as much. One is society. And so there is an increasing demand, I think increasingly desperate demand for solutions to climate change, because it is not obvious how we are going to mitigate it in the 21st century. And I think that actually changes the risk reward scenarios for investors. It changes how people are deploying money. It changes how governments are acting. It brings new opportunities and new models for high risk, high reward research that didn't exist 20 or 30 years, even 10 years ago. And that is enabling different ways of doing things. And then I think, the final answer is what is really different is there are private companies who have raised billions of dollars, who have timelines and boards and budget sheets and Gantt charts and everything else. And those companies are doing things in such a fundamentally different way than federally sponsored science programs that it's unlocking new potential and new capabilities and new ways to track how hard is it going to be? How much are things going to cost? What is the real schedule for a company deploying an energy system? And that is just so different than it was 10 years ago when fusion was essentially the purview of the federal government. So I think I'll leave it at that.
Great. Yeah, so Zach, that ties into a pretty common theme in these questions as well, which has to do with sort of the economics of fusion as we advance the technology. In particular, how it compares or will be able to compare or compete with more established like renewables such as solar power. And to the people who have asked this question, I would also want to encourage you to look on MIT Energy Initiative's website. So we recently concluded a major economic study that addresses this question in much more quantitative detail. It's sort of a spiritual successor to the series of reports on the future of nuclear energy. So we've repeated that for fusion, but with many excellent economists from other MIT departments. So you might also find just more satisfying technical answers there as well. But Zach or Nuno, are you optimistic about fusion's eventual ability to be a competitive economic power source?
Yeah. I'll go quickly and then let Nuno go. And I'll preface by saying that we shouldn't delude ourselves by how hard it is going to be to make fusion work technologically and also economically. It is a grand challenge of the 21st century for a reason. We've made enormous progress, and I think there's significant reason to be excited about all the developments that are happening right now, but it is going to be a hard and complex technology to bring to market. But I'll say maybe two things. I think in order to put a price on something beyond controlling societal factors like carbon cap, carbon taxes, and other things that might change the economics, we ultimately have to build something. We actually have to build the technology in the way that it's going to be deployed into the market, to know what things are going to cost and to understand what the factors of learning are as we get better. There are other examples out there, but ultimately we have to do it. And so what I'm excited about in fusion right now is what I said earlier. It's just there are companies who are now doing these things, and they are using all the tools and capacities of private industry to drive costs down and make things as economically viable as possible. And they will know to the dollar what it costs to deploy these technologies, and will actually get real data. The other thing I was going to say, Sarah, is exactly what you mentioned already. The MIT report is very interesting, not because it makes a prediction for what fusion is going to cost, because essentially that number is so uncertain at this point. What it does is it does two things. It says, if fusion comes in at a certain dollar per installed watt price, this is the benefit to society. So we can basically turn that knob and we can understand how fusion impacts the transformation of an energy system at a societal level, away from fossil fuels. But then the other thing it does is it feeds back into the technologies that we research. And you and I know this very well from Libra, for example, or from the materials, which is we want to be doing research very early on that is informed by economic drivers, because we want to make sure what we're doing today is extrapolated to a technology that's going to be as cost competitive as possible. We want to start that early, not late.
Great. Thank you, Zach. So we have a lot of questions in the chat that have to do with specific technical challenges to fusion. Unfortunately, we are not going to have time to address all of them in detail, but since this is MIT, maybe we can turn our focus a little bit to some of these more nitty-gritty technical questions. So one comment that has come up, Nuno, is regarding disruptions and sort of what is the status of research on disruptions. Maybe you could explain for the audience, what is a disruption? Why is it a challenge to commercial fusion? And then maybe some of the work that we're doing here at the PSFC and in the fusion community to sort of address this challenge.
Great question. So clearly the person who asked that question knows about fusion and some of the challenges. So for everybody else, think of a disruption in very rough terms as the equivalent of a solar flare. If you've ever seen a solar flare, sort of a localized burst in the solar surface, think that the plasma surface in a fusion device could do something like that. And the analogy is not perfect, by the way, but let's just assume it is. And this is a challenge and a worry, because this means that a lot of power could be deposited in the materials surrounding the plasma. And whether you have materials that can withstand that kind of power exposition on a repeated basis is, I think, a very difficult question. And probably the answer is no, that we don't know materials that could withstand a series of disruptions for a long time. And so the common wisdom right now is to accept that this problem is very challenging from the point of view of first principles understanding. So people have been working on this for quite some time and made enormous advances in terms of trying to understand it. But there are still some uncertainties, and we don't feel 100% confident that you can operate a fusion experiment without disruptions. And so what we're doing here at the PSFC right now is trying to develop very sophisticated machine learning algorithms that can be coupled with diagnostics that monitor the plasma in real time and tell you how to operate on the plasma in real time, such as to avoid the disruption. So it's called disruption mitigation and avoidance. And we think that these techniques, these machine learning aided techniques, are going to be essential to operate safely without disruptions. I should also add sort of to this question that disruptions pertain to tokamaks, but not to another concept that people are considering called the stellarator. A stellarator is a version of magnetic confinement that for pretty fundamental reasons would be disruption-free. And people are also looking at this concept as a very appealing concept for future power stations.
Great, thank you, Nuno. So another challenge that has come up in several comments and questions from the participants has to do with radioactive material, how this maybe compares to radioactive material from a fission plant, what are anticipated regulatory challenges that a commercial fusion plant might face, and also like how do we anticipate the regulatory environment might look for commercial fusion, understanding that maybe the current framework that applies to fission isn't really an exact fit for the needs of fusion. So Zach, maybe you would like to speak a little bit about that.
Yeah, sure. It's a great question and timely. Maybe quickly, I think there's sort of three questions embedded in there, right? So on the activation, so materials that are radioactive, I think the first thing to recognize is the difference between fission and fusion, and that in fusion, we actually have a choice about what type of materials get activated. So in the fission process, which people are probably familiar, where we split uranium in order to make power, the radioactive material we primarily are concerned with dealing with is sort of the product, the byproduct of that split. It's the radioactive isotopes that come out of that split. And so in fission, you get that no matter what, because it's an intrinsic part of the process. In fusion, it's very different. The fuel cycle, as you saw, deuterium and tritium come in. Ultimately, what comes out is helium, because that triton is consumed internal to the plant. The fuel cycle intrinsically in fusion doesn't have activated material, radioactive byproducts. But what does get activated is some of the structural materials that are around the device. So essentially that's steel, it's sort of metals. And because we're very clever engineers, we can actually develop better materials, better alloys, low activation materials. And we have a choice about what we activate and what we produce. And so with a number of the material candidates that we hope to look at, for example, in the facility we're building now, the profile of radioactive products looks a lot more like, say, large accelerators or accelerators in the medical isotope production industry than it does like a fission plant. They're just sort of fundamentally different from a physics perspective. The regulation question is a very good one, and it's a timely one because the US, following, also with other nations, but the US has decided that, for example, it will regulate fusion in a very different way than it regulates fission, nuclear power, under different parts of the federal regulation. And that is just recognizing the fundamental differences between the types of materials involved, the byproducts of those materials, and how they're utilized. I think we got through all of that question, Sarah, yeah?
Yeah, I think that's a great answer.
Okay.
Some of our other comments have to do with the various startups, the different confinement approaches that they're taking. And so one thing we haven't really covered yet is inertial confinement fusion. So Nuno, I think that maybe it would be appropriate to speak to some of the major results that we've had at the National Ignition Facility, the role that MIT PSFC has maybe played in that. And then maybe, Zach, if you want to, we could just talk a little bit before we have to wrap up about how, the sort of tokamak/Stellarator approach that some startups are taking, and then versus the challenges that the inertial confinement concepts maybe are facing. So I'll sort of split that up. So Nuno, if you want to maybe talk a little bit about the NIF results, I think that would be really interesting.
So I mean, undoubtedly, one of the key results in fusion research ever has been the announcements from the NIF team that they reached fusion energy gain as compared to the energy actually delivered to their target. So just to remind everybody what we're talking about here, this is something I alluded to in my presentation. This is the concept where you use laser beams, either directly shining on a target or shining on a surrounding material, a surrounding capsule that encapsulates the target, to compress that target down to fusion conditions and then start the fusion burn. And so what they've achieved at NIF was just this. They are not at what we would call engineering break-even, meaning you get more energy out than what you actually get pulled from the grid, but they are at what we call scientific break-even, where the energy you get exceeds the energy actually delivered to the capsule. This was a tremendous breakthrough and just a testimony to how excellent that team is. I don't have time to go into the details of this, but the NIF results are enabled by what are essentially engineering marvels, ranging from laser beams all the way to capsule engineering, all the way to a variety of things. Our team here at the PSFC has a very strong presence in that space historically and continues to have, with many students who then go on to become leaders in that industry. And in fact, one of the campaign leaders for the NIF results is actually a PSFC alumni. And people who are in the inertial confinement-based fusion startup world, some of them are alumni from here. It's a very interesting concept. I think it's one that should be pursued. It's unclear to them, as it is to other concepts, how it is that you actually turn this technology into a fusion power station. But I think it's certainly worth asking the question and doing the research that might lead you there. One thing that we haven't mentioned yet, but which I think is pertinent in this context as well as to previous questions, is that the kind of technology and science that you develop for fusion actually has ramifications in many other areas of science and technology. And so we are in a field where even if fusion takes longer to deliver than you'd think or you'd like, you are developing technology that is very useful in other areas. So Zach Hartwig mentioned geothermal energy. That's one example, but advances in magnet technology tend to benefit many other fields. So I think that's an important point. So I think that was the first part of the question, Sarah.
And so we don't have a whole lot of time, Zach, but maybe, so there are several of the major startups that are pursuing an ICF-based approach. And so maybe you could highlight just a few of the challenges that come with like commercializing or scaling that result to commercial levels, and maybe why the tokamak/Stellarator magnetic confinement approach is maybe seen as sometimes easier for the first generation of fusion power plants.
Yeah, yes. Sort of my lecture one in my fusion undergraduate class, which is great, which is there's sort of all of these different concepts, magnetic, inertial, others. What are they trying to do? The first thing they're trying to do is get above a threshold for performance. They want to show net energy. And the second thing they want to do is they want to get there with the simplest possible concept. And of course, the holy grail is to, get net fusion energy with something which is so simple, it's trivial to see how it makes a power plant. And the tokamak, which we've talked about, followed by the stellarator, have sort of out of the box, if you like, when we first turned them on, enormous performance. And it was sort of seen as plausible engineering, and that the physics performance was very high. Many of these other concepts, it's taken quite a long time and investment, like the National Ignition Facility, to sort of bring those concepts all the way up to the point of producing net energy. Although, as Nuno pointed out, there's questions about how you take the engineering required and turn it into a power plant. So that's what all of these different companies are trying to find. They're trying to find their own interesting trade-off of physics and technology that they think gives them the advantage. And just to directly answer your question, so 2 challenges for NIF, for example. So Nuno mentioned it's lasers imploding these small capsules. The precision with those capsules must be aligned and imploded with the lasers is exquisite. And in order to make a power plant, you have to do that whole process, which currently takes about a day. You have to do that something like 10 to 20 times a second. That's an incredible engineering feat to think about. And also the cost of those capsules has to be made vastly smaller than it currently is today, because the manufacturing methods required to make the precision that you need really pushes the limits of current technology. There's other physics challenges in the lasers and in the glass, optical glass, and other things, but I think those are two easy ones. You have to do something 10 times a second, and that's quite a challenge.
Great. So thank you both. I think we are going to need to wrap up due to time. So I will just say on behalf of the PSFC, how much we appreciate everyone tuning in, all of these excellent questions. And I would also encourage people to look at the PSFC website. There you can find different ways that you can follow along with the progress that we are making, sign up for tours if you're in the area. And so we really appreciate your time, and we hope that you continue to stay involved in checking in on our progress as we move towards this. Thank you.